Good afternoon. So this is the second lecture of the subject Signal System KEC 403. This subject is running in 4th semester of EC branch students for AKTU, and the topic of this second lecture is convolution and LTI system properties. So basically in this particular lecture we will see the operation that is called convolution, and also we will go through the properties of LTI systems. So you know that LTI system is linear time invariant system. So basically there are various properties of in a particular system in which linearity and time invariance is one of the most usable properties. So based on that, systems are defined like LTI systems. And you know, I'm Dr. Amit Garg, Associate Professor in EC Department of AKGEC. So let us move. Okay, so first of all, LTI or oblique LSI system. So LTI means linear time invariant system, and LSI is linear shift invariant system. So these are you can say equivalent terms. LTI is used when we are working with continuous time systems, and LSI is generally used when we will deal with discrete time systems. Okay, otherwise these terms can be used interchangeably also. And you can say these the popular name is the LTI systems for both type of systems. So a good example of LTI system is any electrical circuit consisting of resistors, capacitors, inductors and linear amplifiers. Okay, so if you will make a system using resistor, capacitor and inductors and linear amplifiers, then you can say that system will follow is under category LTI systems. Why we are studying LTI systems? Because these are two important attributes of these type of systems are linearity and time invariance basically. So L for linearity and T for basically the time inverse. So that's why we are studying these LTI systems. And one of the primary reasons for using LTI system for analysis is that such system possesses the superposition property. Okay, so because the linearity is there, so that superposition principle can be applied to these type of systems. Okay. Now, for linearity and time invariance, the output signal must be a weighted superposition of time shifted impulse responses. So this is the condition that for LTI system, the output signal must be a weighted superposition of time shifted impulse responses. Time shifted impulse responses means impulse responses taken at various time instants. It will be shown that the input output relationship for the LTI system is described in terms of a convolution operation. So you can see the convolution operation is like this. If we are having a LTI system, let us suppose this is LTI system, which is having impulse response, let us say HT is the impulse response for this LTI system, and if we are applying input XT to this system and we are getting the output by applying this input YT, then the output can be calculated using YT equals to XT and the operate this. So this operator is called basically the convolution operator, and this process is called convolution. So basically the aim of the convolution operation is to find out the output of the LTI system with respect to any arbitrary signal. We can take any arbitrary signal, and this is applicable both for continuous time systems and discrete time systems. In case of discrete time systems, in place of HT generally we use HN, and in that case the output will be Yn is equal to Xn convolution. Okay, so this is LTI and basically these are the you can say convolution. So Yn, so Yt equals to Xt convolution Xt. When we are doing this for continuous time system, we are calling it as, this operation is calling as convolution integral, and when we will perform this for discrete time system, then it is called as convolution sum. Okay. So the importance of the convolution operation in LTI systems from the fact that the knowledge of the impulse response of an LTI system to the unit impulse input allows us to find its output to any input signal. So basically what happened, let us suppose we have given an LTI system, and we have given an LTI system, and we have to find out the output for any arbitrary input. Let us suppose our input xt is an arbitrary input, and we want the output for this LTI system. Okay. So if we want to calculate the output for this LTI system, for this input which is an arbitrary input xt, then we should know the impulse response of this system ht. Okay. So that we can calculate the yt equals to xt convolution ht. But because we don't know about the impulse response of this system, so what we can do, because it is an LTI system, so what we can do, we will take this system and we will apply impulse input to the input of this LTI system, and we will get the impulse response for this system. And because the LTI system is same, so that we can use this system, this impulse response here, so that we can calculate yt equals to xt convolution ht. So basically by this way we can find out the convolution, we can find out the output of the LTI system for any arbitrary input. So for continuous time system, the convolution operation is defined as convolution integral, and it is defined as yt is equals to xt convolution ht, where xt is the input applied and ht is the impulse response of the LTI system. So this can be written like yt equals to minus infinity to infinity x tau into ht minus tau d tau. Okay, so this is basically the definition of convolution integral, and for you can say for discrete time system, convolution sum is defined, and here we can see this is the expression yn equals to xn convolution hn. Xn is basically the input to this LTI system, and hn is the impulse response of this LTI system, and this, the definition of this convolution is summation k equals to minus infinity to infinity xk into h of n minus k. So this is basically your convolution integral equation, and this is your definition of your convolution sum. Okay. Okay, so this is your convolution integral and convolution sum. So we can find out the convolution integral and convolution sum if we have the input applied and the impulse response. And this is for continuous time systems, and this is for discrete time systems. Okay. Now we will see a question based on finding out the convolution. So we are having a rectangular signal. We can also call it as gate function with itself. So we have to find out the convolution of a rectangular signal with itself. Okay. So you can say this rectangular signal can be defined like this: xt equals to a rect t by 2t. Means you can also represent it like signal. This is your signal, and 2t is the width. So you can say this is minus t and this is plus t. So total width is 2t. Okay. And a is basically the amplitude. So you can say this is the amplitude a. Okay. So you can define like this system as a rect t by 2t, or a, this is the symbol that can be used in place of rect t by 2t, or the definition is like this. So by any way this question can be asked, and it is also sufficient that if in the question it is given that you have a rectangular signal of amplitude a and width 2t. So in that case you have to find out the convolution. Okay. So because here the variables are t, so we are talking about the convolution integral. Okay. So by another way this question can be asked like, evaluate the convolution integral for a system with input xt and impulse response ht given by. So you can see the input and impulse response is the same, and this is the definition for the gate function. So by any way this question can be asked. Okay. Now we will solve this question. So the convolution integral is defined as yt equals to xt convolution ht. Okay, and the definition is minus infinity to infinity x tau into h t minus tau d tau. Okay. So how we will solve this particular type of question? Let us see step by step. Okay. So first of all, what we will do, we will draw the waveforms for signal xt and ht. So you can see this. This is the xt and this is the ht. Okay. Now we will replace this variable t by tau. In one in this equation you can see we have to find out the value xt convolution ht, and which is x tau into h t minus tau. Okay, so we will replace t by tau in both the places. So you can say this is the x tau. We have simply replaced t by tau, which is the dummy variable, you can say, and another one is t minus tau. Okay, h t minus tau. So first of all, what we will do, we will draw h tau. So h tau is nothing but simple like your x tau. So this is your basically h of tau minus t, t and a. Okay, now we will draw h t minus tau, h t minus tau. Okay, so we don't know what is the value of t from which we are shifting. Okay, so let us suppose we are moving. So now this is h tau. So we want h t minus tau. So what we will do? Again we will draw another signal which is h of minus tau. So you can see in this case h tau and h of minus tau will be the same. So this is h of minus tau. Now we will draw t minus tau, h of t minus tau. So you can see this is the figure for h t minus tau. So what happened when we will obtain h t minus tau, then h t minus tau will be look like this. Means what happened, your original signal will be shifted by an amount t, and so it will be, you can say, if it is shifted by t, then let us say this point is t plus t and another point is t minus t. Okay. Now it depends upon the value of t, value of this shifting amount t, that where our signal exists. So now this is our xt and this is ht minus tau. Now we will see that how the regions of these two rectangles overlaps with each other. So for this we have to find out the value of, you can see we have to find out the value of x tau into h of t minus tau. So this is our x tau and this is our ht minus tau. Now we will overlap these two signals. So let us suppose we will fix this signal x tau and ht minus tau. So what happened, what we will do, we will take this signal and we will move this signal over this signal, and we will see the overlapping areas and find out the area of the overlapping signal. Okay, so that will become the convolution. So first of all, the condition, let us suppose first case we are taking, let us suppose we are entering this particular signal over this signal from this way. Okay, so first condition is like that this t plus t point will be exist somewhere here, means you can say this t plus t is less than minus t. So first case is, let us say t plus t is less than minus t. So this will be the situation, this t plus t will be less than minus t. So you can see here between these two signals there will be no overlap, there is no overlap. So when there is no overlap, then the area is 0. So you can say output that we will obtain under this condition is yt equals to minus infinity to infinity x tau ht minus tau equals to 0. Okay, so in this case what happened, there is no overlap, so area is 0. Now what is the second condition? Let us suppose, now we will see that this t plus tau is where lying somewhere in between minus t and t, somewhere lying between minus t and t. Okay, so this is our second case. So you can say this t plus t point is lying between minus t and t. So this is minus t and t, and you can see the figure like this. You can see this is the figure. So this t plus t is the point which is lying between minus t and t. So in this case you can see the overlapping area is this area. Okay, so we have to find out the value of this area. So what is the limit for this? We can see minus t to t plus t. So now the limit will be minus t to t plus t, and the amplitude here is a for both the signals, both the rectangular signals. So what happened, it will become a into a d tau. Okay, so this will become a square t. So this will become if you will solve this, so you will get a square integration minus t to t plus t d tau. Okay, it means a square, you can call it tau minus t plus t. Okay, so when you will solve it, it will become a square t plus t and minus t. So this will become a square t plus 2t. Okay, so this is the output that we will obtain in this condition. Okay, now what happened? Now the next case will be the case when this t minus t will be lying between minus t and t. Okay, so as we are entering our rectangular in this direction, so what happened? Now this situation will occur, then this t minus t will be lying between minus t and t. So this is case number 3. So when you will take this case number 3, so this is the t minus t point, this is the t minus t point, and this time this t minus t point is lying between t and minus t and capital T. Okay, so what is the overlapping region in this case? In this case you can see the overlapping region is basically this region. Okay, so this region is basically the overlapping region. Okay, so what is the limit? So limit for this region is t minus t to t. Okay, so you can see again the limit is t minus t to capital T, again a square d tau, and we will solve it. So we will get a square times 2t minus t. Okay, so we will get this output when t minus t is lying between minus t and t. And the next situation is that when this t minus t point will be beyond this point t. So what happened? Again there will be no overlap. So this is the last condition where we will find that this t minus t, small t minus capital T, is greater than capital T. Okay, so you can see the situation. In this case again there will be no overlap. So if there is no overlap, so what happened? The area again yt is 0. So now you can write this yt as in first case, case 1 we have seen t plus t is less than minus t, so this will become t is less than minus 2t. And in second case you can see t is lying between minus 2t and 0, and in third case we have seen that t is lying between 0 to 2t. So according to this, these are the results that we have written. Okay, and if you will see, then you can represent it also in terms of a triangular signal. Okay, so the convolution of two rectangular signals is basically a triangular signal having width 4t, where 2t is this point and minus 2t is this point, and 2a square t is the amplitude for this triangular signal. Okay, so we can also represent the answer in this form: a square 2t minus mod of t, where mod of 2t is less than equal to 2 times capital T, and 0 when mod t is greater than 2t. Okay, so this is how we will solve the convolution problem. Okay, now we will see the discrete convolution, one numerical based on discrete convolution. So let us suppose the signal xn is given as 0.8 to the power n un and hn is 0.4 to the power n un, and find out the convolution. So we have seen that these are discrete sequences. We will use the discrete convolution, yn equals to xn convolution hn. So the definition is xk into h of n minus k, limit summation k equals to minus infinity to infinity. Now we will put the values here. When we will put the values here, 0.8 to the power k uk, xk will means you will put in xn, you will put n equals to k. So you will get 0.8 to the power uk, and here again h of n minus k, you will put n minus k in place of n. So you will get 0.4 n minus k un minus k. Okay, so if you will see the first case n minus k, if n minus k is less than 0, so you can say there will be no overlap, because this signal is the causal signal, so there will be no overlap. And if n minus k is greater than 0, so you can see there will be overlap, and in this case the limit will be you can see u minus k and u minus k, un minus k means you will draw first of all un, then uk, then u of minus k, then you will shift it. So you can see the limit is somewhat like this. So you can say here in this case, I am not drawing the original signal. So you can say the limit will be from here to here, and this will become 0 to n. You can say. So in place of this, so you can replace this k equals to 0 to n, 0.8 to the power k, 0.4 to the power n minus k. Now because here we are doing the summation for k, so we will take the values corresponding to n outside, 0.4 to the power n, we will take outside and then we will solve, and when we will solve it, so we will get the value, this is the value, 0.4 to the power n, 2 to the power n plus 1 minus 1 un. Okay. So this is basically our output yn, or the convolution between these two sequences. Now come to the topic, relationship between LTI system properties and the impulse response. So basically LTI system properties and the impulse response. So we have to see the relationship between the impulse response and the properties of LTI system. Because the system is LTI system, so you can say it is already linear time invariant system. So now we will see the impulse response, and based on the impulse response we will define another properties like stability, causality, and you can say causality without memory, with memory, static dynamic, all these things we can describe using the impulse response. So this impulse response completely characterizes the input output behavior of an LTI system, or the characteristics of an LTI system are completely determined by its impulse response. Means if we have the impulse response of a system, then we can define its all properties. Means impulse response is itself you can say complete information about a system property. So it is important to emphasize that this property holds is general only for LTI system. The unit impulse response of a non-linear system does not completely characterize the behavior of the system. So here we are discussing about the impulse response. So impulse response means if you will take an LTI system and you will apply a impulse signal to that LTI system, so the output is basically the impulse response. Okay, so this is only applicable for LTI system. This is not applicable for those systems which are non-linear systems. Okay, so hence the properties of the system such as commutative, distributive, associative, with and without memory, causality, stability, invertibility are related to the system's impulse response. Means if we have the impulse response, then we can find out these properties also. Okay, so first property is LTI systems with and without memory. Okay, so systems without memory means memoryless systems. So memoryless systems means we are providing the input to the system and we are getting the output. There is no provision to store the output values, means past output values, or you cannot also store the past input values or future input values. So you can say there will be no memory in the system. Okay, so from the commutative property of the convolution we can see discrete time LTI system can also be defined like yn equals to hn is convolution xn. Basically you have studied yn is equal to xn convolution hn, but it is equivalent to xn convolution hn is equivalent to hn convolution xn because these are commutative. Okay, this operation is commutative. So we will now expand this hk x of n minus k summation k equals to minus infinity to infinity, and now we will expand this equation. So we will see like we are having the values h minus 2, so these values are coming from infinity, h minus 2 xn plus 2, h minus 1 xn plus 1 plus h0 xn plus h1 xn minus 1 plus h2 xn minus 2 plus up to so n. So in this system we can see that for the system to be memoryless, what should be there? This output yn must depend only on xn and therefore cannot depend upon xn minus k for k not equal to 0. Okay, so you can see this is only defined in this case where k is equal to 0. Okay, so when k equals to 0, in that case only it is defined. Okay, so the condition for LTI system to be memoryless is basically hn equals to k delta n, and also correspondingly if you will see for continuous time system it is ht equals to k times delta t. Okay, Second is causality for LTI systems. The output of a causal system depends only on the present and past values of the input. Okay. So again we will take this expression, again we will break it up. So we have represented it divided in two parts, summation k equals to minus infinity to minus 1, then summation k equals to 0 to infinity, and then we have written this, then we have expanded these summations. So now we can see that the past and present values of the input means xn, xn minus 1, xn minus 2 are associated with indices k greater than equal to 0. Okay, so you can see that for indices k greater than 0, we have seen these past values in the impulse response of hk, while future values of the input xn plus 1, xn plus 2 are associated with indices k less than 0. In order then for yn to depend only on past and present values of the input, we require this hk should be equal to 0, okay, for k less than 0. So means all these values, if all these values will become 0, only then our system will become causal. So the condition for causality is hk equals to 0 for k less than 0, and similarly for discrete time systems hn equals to 0 for n less than 0. Okay. Similarly for continuous time system ht equals to 0 for t less than 0. Okay. Then last is the stability. Stability is stable, a system is stable if every bounded input produces a bounded output. We shall now derive the condition of Hn that guaranteed stability of the system by bounding the convolution sum. So we can see that this is the output yn equals to hn convolution xn, then we will take the mod and we will write the definition, summation k equals to minus infinity to infinity hk into x of n minus k. Now we can also write it like less than equal to, because summation because absolute value of summation is always greater than less than the summation of absolute values. Then we can written it like this. And now let us suppose that our input is bounded. So let us, this bx is a finite value. So this mod of xn should be less than infinity. So definitely mod of xn minus 1 should less than equal to bx. So finally, so in terms of mod of yn, we can see like this. So from the above equation, it is concluded that impulse response is absolute summable only if this value should be less than infinity. So if this value will be less than infinity, because this is already finite value, so yn will be finite only when this value should be less than infinity, or you can also call absolute summability. Okay. And similarly for continuous time LTI system, we can see that this convolution integral mod of minus infinity to infinity integration mod of h tau d tau should be less than infinity. Then last condition is invertibility of LTI systems. So we can see here a continuous time LTI system with impulse response ht. This system is invertible only if an inverse system exists. So inverse system is this system that when connected in series with the original system produces an output equal to the input to the first system. So what happened, let's say, so what is the relation? So if let us suppose that this is ht, so basically the relationship is ht convolution hit, ht convolution hit is basically delta t. This is the condition for invertibility. Means if there is an inverse system exists, so you can say the system is invertible. And similarly in case of discrete time system, hn convolution hin, that will be equal to delta n. And in terms of transfer function, if you write hs multiplication his will be equal to 1. Okay. So this is so these are the properties of LTI systems. So I hope that you have understood all these things. Thank you so much.